Okay. All right. Let's take a look. So on Monday we'll have a midterm exam, and so I'll talk about that. Right? Uh, fourth week Monday. I won't give you a practice, but yeah, exactly. I'll give you topics. Okay. Midterm exam Monday. 45 minutes. And then I'll send out a seating chart. Yeah, it'll be in here. Okay. Seating chart Sunday evening. And okay, that's all. All right, let's talk about some topics. Okay, so all right, first up we've got inverse CDF. Inverse CDF, I give a PDF. Okay. And then what you have to do is you find the CDF via integration. It's a PDF. I'll give you a PDF. You find the CDF. You invert the CDF. And then use the inverted CDF to turn U drawn from uniform 0, 1 to X. Okay, so I'll give you U and you give X. Does that make sense? What's that? Yeah, I'll give you like a random U, maybe like a couple random U's, and you turn each of them into random X's. Okay, so that's inverse CDF. You can just make up some PDFs in practice. All right. Okay. All right. Let's do rejection sampling or accept reject sampling. All right. So I will. I'll give the PDF of the target distribution. I'll also give you a proposal distribution. Okay. All right, what you will need to do is you will need to find the appropriate M. Okay. Calculate your expected acceptance rate. And then what I'll do is I'll give you y drawn from g of x, and along with u drawn from uniform 0, 1, and you give the resulting x. Okay. Any questions there? That's all good? That makes sense? All right, let's all right. We have Box-Mueller. So I give U1 and U2 drawn from uniform 0, 1, and you return Z1 and Z2 drawn from standard normal, okay? And then all right, then we got the bivariate normal. I'll provide, I give the desired mu and sigma, okay? You find B and A, and then I give Z1, Z2 drawn from normal 0, 1, and you give X1, X2 drawn from normal mu sigma. Is that all right? Okay, and then we've got Monte Carlo integration for the uniform case. Okay, I'll provide some integral. So I'll provide the h of x, okay, and then I'll also provide a sample of u drawn from uniform 0, 1, or in this case it'll be uniform A to B. And then you return estimates either h bar n or I hat, okay? And then maybe you'll also calculate the theoretic via integration. All right, and so h of x will be simple, like just a polynomial. I'll try to keep all the keep the numbers on the nice side. Yes. I would say number 1 will be fairly simple. The PDF in number 1 And maybe not number 2. So I already have the function in mind. I don't know how to describe it. You'll have to do a little bit of thinking, okay? So yeah, yes.
Should we go over our integration?
So I have a function in mind, and if you try to integrate it directly, it's hard. But if you think about the function, it's there's like a geometric trick, okay? That can okay, and it should make it a lot easier, okay? Not even a trick, but just all right, okay. It should be fine. Okay. Are there okay, any questions? Yes, you definitely need a calculator. Do not forget calculator, all right?
Do you need rulers?
No rulers. Okay. Questions? Anything else? So you definitely need your calculator. All right. Okay. So this covers what we've covered, and I think it covers what yeah, okay. All right. Then okay, so I'll continue on in important sampling. Before I continue on, are there any questions? Homework issues? Stuff? We're all good? 3rd week, we're hanging in there? All right, okay. Next week is Data Fest. We all have our teams and are ready to go. What's that? They haven't told you? No, what?
You don't know if we're in it.
You don't know if you're in it?
No.
All right.
It's like having things well organized.
Okay.
It's nice to know already, though.
Well, okay. All right. Well, I think if you're a senior stats major, you're like for sure going to be selected. But
Even if you've done it before.
okay, you know, I don't know the answers to all these questions. I'm not the one in charge. All right. Okay. I shouldn't make promises that I don't make decisions. So. Well, I'll at least show up and I don't know, give you advice, but not too much. Okay, all right. What are we doing? Okay, we're doing importance sampling, right? Okay, and we said what we want to do is we want the expected value of h of x over the distribution f, okay? So we want the expected value of something like this, and the way this is calculated is h of x times the distribution f of x dx, right? So if it's just like the expected value of some value x, so like so for example, if you just wanted the expected value of x, and x is drawn from the some distribution, that's just the integral x times the PDF of x dx, right? And this is the expected value x, expected value of a random variable x. All right, so this is what we want, and but the problem is we are not able to sample from f of x directly. Okay, if we could, this is what we would do, right? So instead, what we do is we're going to say the expected value of h of x over the random variable f, where x over the random variable x that's defined by f of x. It's exactly this, but we just multiply it by g of x over g of x. So I'm going to divide this by g of x, and I'm going to multiply it by g of x. Okay, and so this remains in the same form of some function. Oh, did everybody respond to the poll here? Okay. This is a function times a PDF, okay? And so this reduces down to the expected value of over g of x, over g of h of x times f of x divided by g of x. Okay, and so so to estimate this, okay, we will draw x1, x2, xn from g of x, okay? And then for each xi, we find h of xi times f of xi over g of xi, okay? And then we take the sample mean. Okay, so we get just 1 over n times the sum from I equals 1 to n of and this will is our estimator for of this thing. Okay. And the intuition behind this is that even though, so when we draw from a different distribution, g versus f, you know, we're still getting random values, but we're going to get certain values of x are going to be drawn too often, and other values of x will be drawn less often, okay? But the difference there is offset by our importance weight, okay? So it's a little bit intuition, is that because we draw x from g of x instead of f of x, you know, we will draw certain values of x too often, okay? This happens where g of x is greater than f of x, okay? these values are weighed less because f of x over g of x will be less than 1, okay? And other values of x will be drawn not enough, okay? This is where g of x is less than f of x, okay? But these values of x are weighed more heavily, or weighed more because f of x over g of x is greater than 1. Yes?
Are there any other requirements other than the domain we talked about last time? Like, does there have to be some degree of similarity between the
No, there's no requirement. It doesn't have to be similar. You'll get better performance if they're similar, okay? Because that means if they're similar, then the values you draw, because you're not going to get to run it infinitely long, okay? So you'll only get to draw it a finite number of times, and that means the finite numbers you've drawn, if they're similar, will resemble what you want. If they're vastly different, according to this, in the long run, it works out. But in the short run, you know, even after like 10,000, 100,000, even 1 million samples, what you've drawn may not represent what it is that you're looking for. And so certain values are going to be weighed a lot heavier, and other values are weighed a lot less, okay? And so so basically your estimate's not going to be as good because your perception of the thing is based on your, you know, just whatever else it might be, right? So yeah, I don't know. Okay, so right. Okay. All right. So let's take a look at maybe an example here. We'll just try it out for. We'll do the folded normal again. Distribution. Okay. So our desired f of x is equal to 2 times the regular normal PDF for x in 0 to infinity. Okay, because we're just looking at this half, right? Okay, so this is going to be 2 times 1 over root 2 pi e to the negative x squared over 2. That's our normal thing, and let's say we just want the expected value of this distribution. Okay, so the expected value of the normal is 0, but if we're only dealing with half of it, what's the expected value of that? Okay, so basically we want the expected value over f of x, which is going to be equal to the integral from 0 to infinity of x times our PDF, 2 times 1 over root 2 pi e to the negative x squared over 2 dx. Okay, and I know we covered methods on drawing from the normal PDF and all of this and stuff, but we're going to say we don't know how to draw from this thing, okay? And instead we'll draw from the exponential distribution. We can change up the exponential just for kicks and things like that. Okay, so this is what we want. Okay, we're gonna we pretend that we cannot. We pretend we cannot draw from the normal distribution. Okay, so instead, we draw from g of x, which will be the exponential, and we'll use lambda equal to 2. And so g of x has the form 2 times e to the negative 2x. Okay. All right. So what we have now is so our expected value of x, which is equal to this. This becomes the exponential distribution has the same domain, so we're fine there. And then we just throw this thing into the numerator, and we throw the other part right there. Okay. And so so now we can approximate this, or not approximate this. This is exactly this. Is going to be x times this mess. I need a bigger parentheses. All right. So I'm going to try to do. Oh, I'm sorry. This is I left off the 2 earlier. Sorry. Okay. So let me just do a little bit of work here, and I'm going to get 1 over 2 pi, and then here I'm going to have e to the negative x squared over 2 plus 2x. All right. Okay. And now here, x is drawn from the exponential distribution with lambda equal to 2. Okay. So to estimate the expected value of x of the folded normal, what we will do is we draw x from the exponential with lambda equal to 2, and then we calculate x times 1 over root 2 pi e to the, so this is going to be x of I, negative x of I quantity squared over 2 plus 2 times x of I. Okay. And then we take the sample mean. Okay. Is that all right? Let me, I just want to do a little talk about kind of similarities but differences between rejection sampling and importance sampling, okay? So again, importance sampling, we should think of it more as like weighted Monte Carlo integration or weighted Monte Carlo estimation here. All right, so let me just do All right, so in rejection sampling, the goal is we want values of x which are drawn from f of x, okay? So the goal is we want the actual values of x, okay? And we say we can't draw from f of x directly. So what we do is we propose values from g of x, and either we accept or reject the proposed value based on f of x over m times g of x. So that means some values are thrown away. Some proposed values get thrown away. Okay. With importance sampling, the goal is not values of x. The goal is we want to estimate the expected value of some function h of x, where x comes from f. Now, if importance sampling did not exist, we could use rejection sampling. Like if we can't draw from f directly, what we could do is we could use rejection sampling and use a resulting sample and not do importance sampling, but just do regular old Monte Carlo integration, the general case where we've drawn from f. So we could use rejection sampling to get a random sample from f, and then use that to estimate this thing here. Okay, but that again, that would involve throwing away some values. With importance sampling, we're saying, well, you know what? I don't actually care about the actual values of x that I've drawn, and perhaps each value of x that I draw could provide some insight to what it is that I want. And so what we do is we still propose from g of x values from g of x instead of f of x. But instead of just throwing away these values, we weigh their importance to be less, okay? We use every value and but we weigh their importance differently. Okay. So in kind of our diagram, all right, so maybe we have normal distribution like that, and maybe we've got the exponential distribution, something like this. Okay, this is not a good picture, but basically, let's say we're at this this point right here. Okay, so this is some proposed value here. So according to rejection sampling, is maybe I don't know, 20% of these values get thrown away. Okay, so with rejection sampling, this value gets thrown away 20% of the time. Okay. With importance sampling, I'm going to just call it weighted Monte Carlo. We don't throw away any values. We just weigh them 20% less in the calculation of the expected thing. All right, is that okay? Okay, let me just kind of demo what we're going for. All right, so okay, so what we want is again folded normal. All right, so here will be so the theoretic answer is the square root of pi over 2, I believe. Or square root of 2 over pi. Okay. So the theoretic answer is this. Okay. 0. Okay. Here we can do a regular Monte Carlo estimation by sampling directly from the desired distribution. Okay, so how would I do this? I'm just going to do z, so we'll just do n is 1,000,000, and we'll say z is r norm n, and then z will be, I'll call this z positive. We'll just do the absolute values of z, and then we'll just take the mean of z positive. Okay, and we get something pretty close to, here, I'll set a seed here, just so if you do it, okay, so that's pretty close to the theoretic value, okay? And that's a regular Monte Carlo estimation by directly sampling from f of x. We're able to do this, okay? We're going to pretend now that we can't, all right? Okay, so we'll do importance sampling, okay? We can't sample f of x directly. All right, we sample g of x. Okay. All right, so f we'll write to be a function of x, and it will be 2 times the normal density. Okay, and g will be a function of x, and this will be the exponential of x with the rate equal to 2. All right, so what should I do? My x will be a random sample from the exponential, so I'll do r exponential, we'll ask for 1,000,000 of these values, rate equals 2. Here, let me set the seed to 1 again. Okay, so I have now 1,000,000 exponential values. Okay, and then what do I want? I want to take each of these x values, and then I'm going to weigh them by doing f of x divided by g of x. And then what do I do with all of these values? I'm just going to take the mean of them. And we get something pretty close to, okay? And I don't know, it's not that impressive, but that's what we have here, okay? So it's just, so in this case, you know, we're going to say we can't sample from this thing directly, and so instead we sample from something else, and we weigh them. We weigh it accordingly. Okay. All right. Are there any questions on this? And so, you know, here we're using things where the PDFs exist nicely in these built-in dnorm and d-exponential functions. But I mean, we could have some kind of crazy distribution, right? I don't know, whatever else it might be. Okay, you can have some kind of crazy function that you're trying to estimate, and again, you can use importance sampling to approximate this a little bit better. Okay. So I think the next homework, which I haven't released, we'll probably release it after the midterm, will show up, and you can do one of the questions there will be importance sampling and all of that. Okay, yeah. I think I got to cover some more stuff here, so we'll do importance sampling and then a few more topics. You'll see your next homework. Okay. All right, we'll see you guys on Monday, and good luck as you study for the midterm, and we'll see you then. Okay, have a good weekend.